Okay, welcome. This is the third class for EDS 521. Today we're going to be talking about the normal distribution or the Gaussian distribution, and it's really fundamentally one of the most important pieces of inferential statistics because it's in large part it's the theoretical distribution of scores that all inferential statistics are based from, or most all. So we're going to consider some of the properties of the normal distribution tonight, and some of the ways that that's used to help us to account for what proportion of the cases are accounted for. But before we begin with that, I want to go back and revisit the concept of standard deviation. And as you recall, standard deviation we talked about informally as being the average deviation of scores around a mean score. And that's not technically true, but I think it's conceptually pretty valid, and it's certainly a helpful way to consider what standard deviation is. What's important to focus on with standard deviation is the fact that it reflects the underlying metric. That is, it's in the same scale as whatever your original test or measure was in. So just like your individual scores on a test and the mean, the standard deviation is in the same units of measurement that you use for your test. So again, if we think about standard deviation in the normal distribution or the normal curve or the Gaussian curve, we already learned that we could account for 68% of the cases in plus or minus one standard deviation. So if we go from minus one standard deviation to plus one standard deviation, you'll see that that is cumulatively 34.13% below, another 34.13% above, total of 68% within one standard deviation of our mean score, 0, right? Again, if we go out another standard deviation in each direction, notice that we pick up another 13.59% of our cases are represented in this amount of area. This is 13.59% of all the area that's underneath this line or the curve. And so when we speak about area under the curve, we literally mean how much area is represented, say, between this standard deviation minus 2 and this standard deviation minus 3. In this case, we see this is 2.14% of all the area that's represented under the curve. This is an important concept because in the use of the normal distribution or the Gaussian curve in doing inferential statistics is we're trying to determine the probability that something happens. Everything is about probabilities. So what proportion of cases is accounted for tells us how likely it is that something is in that area. So is it likely that someone, for example, is more than minus 3 standard deviations on this measure? Well, we know that only 14/100ths of 1% are accounted for in this area of the distribution. Similarly, if someone has plus 3 standard deviations, or something that is, again, is only 14/100ths of 1%. That's 0.0014 as a decimal. Now remember, this is expressed in percentage. So you've actually got to add 2 zeros here to think about how small a number this is. It's a very small proportion of all cases. There are several things that I think are really critical. And so if you're taking notes, and I hope you are, 3 things that I think you should really try to account for as you think about this. Number 1, the underlying characteristic, whatever it is that you're measuring, can vary equally in both directions around the mean. So whatever your mean score is, doesn't matter if this is the weight of rutabagas or if this is the score on an IQ test, whatever the mean is, around that mean, scores can equally vary. In other words, it's equally probable that a score is higher than the mean as it is that the score is lower than the mean. The second one is that there is some precision in measurement. So we can expect to find a fairly precise central measure, and then we can, in fairly small increments, we can measure up and down deviations from whatever our average or our mean value was. And that the error in our measurement is equally distributed too. So when we take rock samples, we don't systematically take rock samples that are larger or smaller so that we don't have a skewed distribution. So as long as we have these caveats in place and we don't violate any of them, we can use this normal distribution to predict the probability that an event is going to happen. So let's continue on to the next slide. So again, in a normal distribution, about 2/3 of the scores, a little more than 2/3, are within one or plus or minus one standard deviation of the mean. And we see that roughly 95% of all scores are within 2 standard deviations of the mean. Now, this idea of plus or minus 2 standard deviations, or actually it will be a number close to that, plus or minus 1.96 standard deviations, we're going to see is an incredibly important number in statistical hypothesis testing later on in this course. So that's a number that should stick in your mind. Two numbers, 1.96, that's 1.96 standard deviations up and down. So just below plus 2 and just above minus 2. And that happens to coincide with a concept where we have exactly 2.5% of the area below and 2.5% of the area above. And that leads us to have 95% captured between plus or minus 1.96. More about this later, but I just want to give you a little foreshadowing. That's an incredibly important number. You can lock that away in your head. So a standard score is a derived score. It's a score that can be calculated with just 3 pieces of information. And it's very useful if we have the assumption of normality. We have the assumption that we have a normal distribution in place. A standard score is a very useful way to look at any individual score and be able to interpret it in terms of how did this person or this thing compare with the average. So in this case, we have to have our score, we have to have our mean score for our distribution, and we have to have our standard deviation. With these 3 pieces of information, we can find our standard score. Any standard score expresses performance relative to the mean and in standard deviation units. Okay, that's a very important piece to remember. And a standard score is calculated with those 3 pieces of information: the score, the mean score, and our standard deviation. So the simplest kind of standard score is called a z-score. And a z-score is nothing more than our observed score. Okay, so Billy got 110 on a test, or 115, let me correct myself. And the mean score is 100. And the standard deviation is 15. So for those of you that are already onto this, you can jump ahead just in your head, and you can figure out that an observed score of 115, take away a mean score of 100, divided by 15, that leaves 100, take away 115, take away 100 divided by 15, and we have a z-score of 1. So let's actually just go through an example here. So, for example, if our mean score was 10 and our standard deviation is 2, then if x is 12, if our observed score is 12, what is our z-score? Well, we just have to substitute those numbers in. And what do we find? Well, let's calculate it. So let's substitute some of these numbers in. If our observed score is 12 and our mean we said was 10, I'll have to excuse my mouse drawing here, and we divide by our standard deviation, in this case is 2, And of course this simplifies to 12 minus 10, simplifies of course to 2, and of course 2 over 2 is 1. So the formula for calculating a z-score with simple numbers you can do in your head. With more complex numbers, of course, it's a very simple formula. You can plug them into a calculator, and you can determine what your z-score is. The z-score is the simplest because it gives you the score in terms of what? In terms of standard deviation units. So standard deviation units and z-score units are the same. They're the most direct type of standard score. A lot of times people have a hard time understanding z-scores or consuming z-scores at a consumer level. And so we will transform these into lots of other kinds of scores, which I'll discuss in a couple of minutes. Z-scores are helpful because they always have a mean of 0 and they always have a standard deviation of 1. And if you think about this, it makes intuitive sense because our z-scores are based off the idea of the normal distribution, which always has a mean of 0, and we have standard deviations going up in ascending order and descending order. They are, in fact, the same as z-score units. So if you see something expressed as a z-score, you can know a couple of things about it immediately. It always has a mean of 0, and it always has a standard deviation of 1. And that is regardless of the original mean, the original standard deviation, or even the shape of that distribution. Now, we can have z-scores with a non-normal distribution, and we'll get to that more in a little bit. But an important piece for you to remember is that a z-score is really just an expression of someone's performance in terms of standard deviation units in whatever test or measurement that you might be considering, someone or something. This could be weight of rock samples, it could be size of tumors, it could be again, scores on an IQ test, any kind of measure where we can find a mean, a logical mean, and then we can look for sampling error around that, we can see z-scores, and we can determine how far someone or something is from the average point in that distribution. So what are some of the uses of standard scores? Well, why would we go to all this bother to generate these things? And it's really about expressing someone or something's relative performance. That is, relative to whatever else is in that distribution. It's also good for comparing performance across two variables that have different means or different standard deviations. By transforming scores into z-scores, that is, by taking somebody's raw score and comparing it to the mean of a distribution and expressing it in standard deviation units, we now have a measurement system that we can use across many tests, we can use across many situations, and we can compare them in a more logical fashion. Now, there are, again, caveats to that as well. However, it is important to note that this is how most kinds of comparisons are made across multiple measures, is by first transforming things into z-scores. It's also helpful in that we can combine two variables into a single composite score. So we might have mathematics ability and reading ability, and we want to put them together. Well, maybe there were 60 problems on the math test and there were only 40 problems on the reading test. We can't logically add the raw score performance together. We have to first transform both scores into z-scores before we can combine them, or we can average them. It's also, as an expression of relative performance, if you have a z-score of plus 1.50, what do you know? Is that good? Is that bad? If you're a z-score of minus 0.50, is that good? Is that bad? Is that average? And what about a z-score of 0? Is that good? Is that bad? Or is that average? Okay, so if you said that z of plus 1.50 is above average, you're right. You're doing significantly better than most people, the majority of people. If you said z of minus 0.50 is somewhat below average, you'd be mostly correct. It's low average, perhaps. It's not really way below average, but it is certainly below the average of the distribution. And if you said z of 0 is average, you'd be right. It's right in the middle. So let's look at a couple of examples here. So looking at the comparing across a couple of variables having different means and standard deviations, here's my example of a mathematics reasoning test which has 60 items. It has a mean score of 30 and a standard deviation of 5. Maybe we have a verbal reasoning test that has 85 items. Okay, so notice that this is expressed in y bar instead of x bar, just to demonstrate that we've got two different distributions here. So y bar is 50, the average score is 50, and our standard deviation is twice as big, it's 10. You can't compare these two things directly. So for a particular student, they got an x of 35 and a y of 40. What's your conclusion? Well, it's difficult to tell without first transforming these into z-scores, because really what you're asking is how did they do compared to everyone else. But on the two tests, they are certainly different metrics. So let's take a look. If we look at the math score, we see that they got a 35. Now 35 is less than 40, yet their z-score for math was plus 1.0. For the verbal reasoning test, notice that their y was 40, but the mean score for y for the distribution was 50. They were minus 1 standard deviation, whereas they were plus 1 standard deviation up here on the math reasoning test. So raw scores don't tell us anything. We have to first transform them into the relative performance against the underlying distribution. In this case, this child was certainly much stronger in math than they were in reading. That's despite the fact that their math score was lower than, their math score was lower than their reading score. So we could combine variables into a single composite. We could create a total score by taking the mean z-score for each student. So for our previous student, remember we had plus 1 on math and we had minus 1 on verbal. If we were to average those together, we would of course get 0 divided by 2 is 0. So z-scores, as I said before, I think are difficult for a lot of folks in a more consumerist situation or context to understand. So t-scores are really just transformed z-scores. A t-score is a z-score times 10 plus 50. So if we took a look at how this works, we see that t-scores always have a mean of 50, and they always have a standard deviation of 10. Again, they're standard scores, they're very predictable, and they allow someone to look at performance in the same way as a z-score, but what's different about them is that they don't have 0 as the average point, and 0 is kind of a problematic average value in some situations. So in the book it used the example of a moral reasoning test, and if your child was average, they would have a z-score of 0. That would be perhaps a difficult or unpalatable thing to explain to parents, that their child's moral reasoning or moral a measure of their moral compass, if you will, it yielded a score of 0. That would be perhaps disturbing to a parent. So to counter this, statisticians and measurement folks have developed other metrics, and one of them is this t-score. And what it does is it, instead of having 0 as its balancing point for the average, it has instead the score of 50. And it's stuck with a very simple standard deviation as well. It's always 10. So if we look at this, we see now we have z-scores. Z-score of 0, of course, is 50, plus 1. If we go back to our formula, it is, got to click on the right place. Our formula, remember, for a t-score is the z-score times 10 plus 50. So if the z is 1, 1 times 10 is 10, plus 50 is 60. And if we look ahead, we see that, in fact, that is the case. T and z are linear transformations of our raw scores. There are other standard scores, and you'll see these often if you look at tests and measures that are used in schools. For example, we looked at z-scores and t-scores, but there are also SAT scores. SAT scores are really nothing but t-scores that are multiplied by 10 again. So you'll notice that the mean for the SAT or the GRE is 500 instead of 50, and instead of 10, it just uses 100. It's the same thing. Wechsler gives us standard scores that are expressed as 100 as average. So if you hear of like a Wechsler IQ, that's 100 as average, and then it uses standard deviation units of 15 as the standard deviation. Whereas the Stanford-Binet IQ scale is still 100, but it uses 16, just a small difference there. Okay, so this brings us to Appendix C in Table A, which begins actually on page 448 in your textbook. And it's everything you ever wanted to know about z-scores in the area under the normal curve. One of the things that you need to remember is there is an assumption of normality, and we're going to just simply operate under that assumption during this course. However, it's rarely the case that we have a truly normal distribution in reality. We often have to make some kind of adjustments. So Table A is really the standard normal distribution without any of these other kinds of adjustments or assumptions. And again, remembering that these are the characteristics where we can account for 99.72% of the cases within 3 standard deviations of our mean. So let's look at a little section of Table A, just so I can explain what it is that you're looking at here. The first column here, Z, is the observed z-score. So remember, Z here is that average. All right. So I'm going to just informally draw a little distribution over here. Very poor. That's a positively skewed distribution. Let me try again. I may need a couple of them here anyway to help me. Oh, that one there doesn't have too much variance. It'll get the job done. So a z-score of 0, remember, is the center. And we can see that this table goes up in very tiny increments. All right. Now notice the break here, because it's obviously there's a jump between 0.02 and 0.75. So 0.00, there is no area between the mean and the observed z-score, because the mean is 0 and the z-score is 0. So there's no difference. And how much area is beyond z? Well, in either direction, in this direction, beyond z, it's considering it in the positive, there is 50% of the distribution is beyond z, right? Let's look down here. I'm going to skip down to plus 1. If we think about plus 1, we can see that now only 15.87% of our distribution lies beyond that observed z-score. And it must be true, 34.13% of the distribution lies between the mean, okay, so between here and here, between 0 and plus 1, lies 34.13% of the distribution. That's this area right in here. That's 34.13%. And you'll notice that this number and this number always equal to 50%, or 0.5. This applies to positive or negative z values alike. So let's look at another example. So another one of the uses for a z-score is to determine the area of the curve that's represented by that score. So, for example, if we look at a positive z-score, for example, a z-score of plus 0.75, we can see that the area beyond or above. Now let's just kind of illustrate again what it is that we mean by that. So if we think about the normal curve, plus 0.75, this of course is z of 0. So plus 0.75 is going to be roughly here. We want to know what is the area beyond that score. So what is this area here? In this case, we can see plus 0.75, the area beyond it is 22.66%. What about a negative z-score? Well, we have the same thing, but this time remember we're looking for the area beyond. So this is a critical point, and if you don't catch this and you don't already understand this, it will really screw you up with this whole section. So this is z of 0, remember. Negative 1 is down here, so negative 1. This, we want to know what is the area falling above a z-score. Alright, so in this case, we have negative 1, so we have to take the area between the mean and z. That's going to be 34%, 34.13, and then we also know that above a z-score of 1 is also all of this area. So when we add 34% together with this side, which is 50%, we get how much? Approximately 84%. 84.13% in fact. Now, there is a good website that I think that you should either after this video or right now pause this video. It's gotten a long way into this and it's been very long. This is a very involved chapter, and it's the foundation for pretty much everything else that happens in inferential statistics later. So it's why we're spending an inordinate amount of time on this. For those of you for whom this is review, I apologize. But for those of you for whom this is your first course in statistics, do not skimp on this chapter because it is so important. So we can also determine area given z for the area falling below a z-score, as we just mentioned. So for example, if we have a z-score of plus 0.77, we can see here that we have the area between the mean and z. So if we recall that what we're looking for is in this case we've got 0, of course. This little thing should be pretty familiar to you at this point. So let's say that this is plus 0.77. Now we want to know what is the area falling below that z-score. So in order to find that, we need to know the area between the mean and z, so between 0 and plus 0.77, and we find that that's 0.2794, 27.94% of the distribution falls right in here. But that's not all. We also have to remember that we have the entire bottom 50%. And so when we add that together, what do we get? 77.94% of the curve falls below z. How about a negative z-score? We can do the same thing. So again, if we look at our little sketch and we think a negative z-score of minus 1.02, if we look here, we see that the area beyond z, that's below it, that's beyond it, is 0.1539, and that's this area right here. Very simple, very easy, but these are extremely important concepts. Now, we can also look for the area between two scores. Now, you saw that that was a feature on the David Lane site as well, and again, you can use it to check your work. So we can look at what is the area between two positive scores, for example, between plus 0.75 and plus 0.10 or 1.00, excuse me. We can also do two negative scores, or we can do mixed signs. So, for example, if we take two positive scores, we see that the area beyond plus 0.75 and the area beyond plus 0.100 plus 1.00, the area beyond it, is 15.87%. 0.75, the area beyond that, is 22.66%. If we subtract 15.87 from 22.66 or 0.2266, we get 0.0679. There is 6.79% of the distribution lies between a z-score of 0.75 and a z-score of plus 0.100. So again, just to graph that, if we think about these two scores, like let's say that this is plus 0.75 and this is plus 1.00, we're just asking what is the area between those two scores. Hence why we subtract this area that's beyond plus 1.00 from the area, the total area that's beyond this. Let me draw that again a little bit bigger, okay? Because this is again, if this is review, I apologize, but for those of you for whom it's not, so again, we have plus 0.75, might lie right about here. Here we have plus 0.100, maybe, actually, this is more like 1.00, maybe 0.75 lies right about here. So there's our 0.75, that's this first line. And then the second line here, plus 1.00. We know that from over here that the area beyond this is 22.66%, but that includes all of this. We only want to know about this area right in here. And so we therefore need to take the area that is beyond 1.00 and subtract it, get rid of this, from this total up here. And that leaves us with this, 0.0679. If we use two negative scores, we just repeat the same process. It works exactly the same way. But for mixed signs of z-scores, the process is a little bit different. So for example, if we want to know what's the area between minus 1.00 and plus 1.00, well, in this case we're taking the area between the mean and z of minus 1.00, which is 0.3413, and plus 1.00, which is again 0.3413. And when we add those two together, we get 68.26% of the distribution. Again, just to sketch it quickly, we remember that minus 1 and plus 1. So the area between the mean and z, so here's our mean, 34.13% and 34.13%, and that's what we're doing to calculate this. So let's take a little break here, and why don't you do a little bit of calculating for me, and this is just for your own edification. So if you really want to get the maximum value out of doing this, you'll pause the video and you'll answer a couple of questions here, and then restart the video after you've got your answers in front of you, and this will help you check and see your own understanding. So this is where you should pause, and we'll pick it right up. Okay, so hopefully you paused and you were able to find these values. So what z-score above which 5% of all cases falls, what z-score below which 5% of all cases fall, and the two scores between which the middle 95% of all cases fall. So if we look carefully, we see that there's these are called critical values, by the way. A z of 1.65 we see has an area between the mean and z of 0.4505 and the area beyond z of 0.0495, which is the closest that we can get in Table A in Appendix C to 0.05. Okay, that is the closest value that we have. The second question, which is between what two scores do 95% of all cases fall, and if you remembered my earlier hint, you probably got this. If you found the z-score of 1.96, you'll see that the area beyond z is 0.0250. If you have 0.0250 in both tails of the distribution. So if you have, that's 2.5% down here, and you have 2.5% down here. The total of that, of course, is 5%, and therefore 95% of all cases fall in the middle of our little mountain here. All right, so this is our 95%, excuse me. And we can use Z to determine the area between cases or beyond cases. So later in the course, we're going to go back to what are the implications of this for probability and probability distributions, as well as what we call statistical significance. In other words, what is the chance that something happened by chance alone versus that there was some effect that was measurable. So what about standard scores and non-normal distributions? Well, standard scores are handy even with skewed distributions. They help you to understand somebody's relative performance to a group. But you can't use skewed distributions to determine the area under the curve. Those kinds of calculations and assumptions are no longer valid. So let's move on to a little bit about effect size and the normal distribution, and looking at what an effect size represents. So in the last chapter we talked a little bit about effect size differences, which are pooled standard deviation differences between perhaps two groups or two measures. So take for example the case of an effect size of plus 0.50. Well, in an effect size of plus 0.50, we see in this case we have a mean for group 1 of 48, a mean for group 2 of 53, and we see that our pooled standard deviation is 10 in this case. So if we take our effect size formula, we take 48 minus 53, which is negative 5, and we divide that by 10, which of course is 0.5, and in this case the sign is negative 0.5. So if we look at these two distributions, they're offset by one half of one pooled standard deviation unit. So what does that mean exactly? Well, 69% of, at the 50th percentile for distribution 2, which was their raw score average was 53, that is the 69th percentile for distribution 1, whose raw score average was 48. Another way to say this is the average person in group 2 falls at the 69th percentile of the group 1 distribution, or the person at the 69th percentile in group 1 falls at only the 50th percentile, or the average value of group 2. So if we go back and we look at that, we can see that both of those things are true simultaneously. So for example, again, look at this person in distribution 2 who's gotten an average score of 53. They're only average in their own distribution, but they're at the 69th percentile for distribution 1. Likewise, a person in group 1 has to be at the 69th percentile to just be average in group 2. That's the half standard deviation difference between these two things. There's a 19% percentile difference in the distributions in terms of what the average scores are. So why is this important? Well, before we go on to some of the characteristics of percentile ranks, it's very important for us to understand how big the offset is between the performance of different groups. Perhaps we want to check the effectiveness of an educational intervention. So let's go back to our little offset distribution. If this was the performance of kids in an intervention, or say in distribution 2, versus kids not in the intervention, we might then conclude that the intervention had some effect. Or if this was girls in distribution 2 versus boys, we might say that girls were overperforming boys. So these kinds of offsets, these kinds of differences observed in distributions are important for interpretation purposes. We're not going to talk too much more about that today. Let's skip ahead. Percentiles, as you may have already read, are non-equal intervals. So percentiles have, in fact, unequal intervals or units in terms of the underlying performance. The number of items correct, the number of score points, and this is inherently true because of the normal distribution. So, what I want you to see is we have our standard deviations, of course, are evenly spaced in terms of raw performance. Okay? Each raw performance gain leads to is an equal distance in standard deviation units. But in percentiles, it's very different. 50% of the people, of course, are above, and 50% of the people, of course, are below. That is, by definition, what a percentile rank is, of 50 percentile. Notice how the percentiles are clumped in the middle. We go all the way from the 30th percentile to the 70th percentile in this small range. And notice how they are really spread out in the tails. We only go from the 1st percentile to the 20th percentile in all this distance. Same up here. So think about this. Here's the number correct on a 25-item vocabulary test. And we're going to assume a large and a normal distribution. So we start out down here at just 2 correct, go all the way to 22 correct. The average person got 13 right, notice. Okay? Each of these two boxes captures a 20 percentile point difference. But box A is equivalent to a difference of 8 words correct. That's a big performance difference. So we go all the way from 3 all the way up to 10 in box A. However, in box B, with same 20 percentile points, we're only 2 raw score point differences. Now, why is this? Well, consider the 10 percentile point gain. In the middle of the distribution where most people are, this corresponds to a p-value from a p of 45 to a p of 55. In terms of the Stanford Binet IQ points, this is a gain from 98 to 102. It's only 4 points, or 1/4 of a standard deviation. However, if we go out into the tail of the distribution, where there are only a few people, remember, the curve gets thin out in the tail. That thinness stands for there aren't many people out there. A gain from a p of 89, a percentile of 89, to the 99th percentile represents an IQ gain from 120 to 137. That's 17 points, or more than 1 standard deviation. So we went from 1/4 standard deviation to make the same 10 percentile point gain in the middle to more than 1 standard deviation gain to make the same 10 percentile point gain out in the tail. So here's another way to think about this. It's like going down the road and to see how far you have to go and to pass 50 houses. Think of this as gaining in percentile points. You're going past other people that you're being tested against. In a populated area, where you might think of this as the middle of the normal curve, it's where most of the people are, you could drive only half a mile and you would pass 50 houses. But out in the rural parts of, say, Maine, northern Maine in particular, you might have to drive many miles before passing 50 houses. So the mailbox analogy, I think, is a good one. If you think about where people live and where people don't live, it's easier to go by folks when there's lots of them clumped together. All right, so here's the final slide, and I want you to consider the following 2 scenarios. And this is on your own time. But I want you to just imagine, this is the sense-making piece of this. Remember, statistics are not just for measuring numbers and writing journal articles. They're for interpreting information. I want you to imagine for a minute you're a 7th grade teacher. And even if you're not going to be a teacher, you can imagine this. And a parent calls and says that they're concerned about their son's drop from the 60th percentile in the 6th grade to the 40th percentile this year. He seems to be keeping up in class, and his scores are good otherwise. What kind of statistical interpretation would you make? Imagine that you had the same 7th grader, and he went from the 11th to the 1st percentile on his math scores. What statistical interpretation would you make there? So, are they each relatively important, or is one more important than another? And how would you explain that? How would you talk about it? Okay, so that's it for this lecture. It's been a really long one, and I apologize, but this is very important stuff. I'd encourage you, if you need to go back through it, look back through examples. Please spend some time on the David Lane site, and if you have questions, do not hesitate to call me or to email me. Okay, we'll see you next time. Take care. Bye-bye.